Hello. Hopefully everyone's doing okay. We're working on lab 10 today. There's exceptions here, so we've talked about exceptions, but there's one other technique that you're going to see me doing that I haven't talked about in code. So I'm actually going to start by showing you that and explaining to you what's going on. And I guess arguably you could say there's two techniques. So if we look at the lab is implementing this singly linked list class, and there's a set of functions starting out inside of it. But the thing I want to talk about is what's going on down here. So I've nested a struct defining a node inside of the singly linked list. And the reason I've done that is because the only place where I really need to make references to a node is in this class, which I will be writing functions to manage a set of nodes. So if you remember on Tuesday, if you were here, if you watched that video, I said that in a way there is no such thing as a linked list, because it's really the linked list is really just a set of nodes that are chained together, and each node holds a piece of data. But this linked list that we're working on today, the point of it is that we need some way of managing that set of nodes. Just throwing a set of nodes out there into memory isn't nearly as useful if we can't access them, if we can't inspect the data that's inside of the nodes, if we can't add new nodes and chain them together. So what we're doing is we are creating a singly linked list class that still really isn't the data, because the nodes are still the data, but the singly linked list class will allow us to gather together a set of functions and manage a set of nodes. So that's why I've embedded the struct definition in the class, is because I don't really need the node outside of the class that I'm creating to manage it. But the other thing that you'll notice, and I'm going to separate this out into a separate piece of code here in a second, I've got this whole definition. So I've actually defining a node with two fields, a pointer to another node that I call next, and then an integer data field that I call value. And then I also have a constructor that allows me to build nodes with values. But then at the end of that definition for a struct, I actually create a pointer to that struct that I call head. So that head piece is a linked list concept, but I want to talk about this, what I've done with this struct here. So I'm going to bring up another piece of code real quick and just show you what it is that I've done. So in C++ code, you can create structs, of course. I'll call this one box. Okay, it's like string name, float weight. And then in a program, I might create a couple of boxes, B1, B2, and C++ can figure out that what I'm referring to when I say box is this struct type that I've defined above. But an option to that is at the moment that you define the type, you can actually begin declaring variables of that type. So in this case, what I've done is I've also made B3, B4, and B5, which are all boxes based on that struct. Just like B1 and B2 are, it's just a different way of doing the setup. Another thing I can do, though, is I can say star pbox, and what pbox now is a pointer to one of these boxes. And we're going to be using pointers a lot with linked lists, so that's what that means. Pbox is, well, I'll call this pbox 2. That's no different than box star p box 1. So pbox1 is a pointer to a box, pbox2 is a pointer to a box. Now, when I have a pointer set up this way, I can move that pointer around. I can put it next to box. I can put it in between them with a space. I can butt it up against pbox1. When I am declaring a pointer immediately after a struct definition, I need to put the pointer near the thing. I can put a space here, but I need to put it near the thing that's a pointer, because if I move that star over here, then only B3 is a pointer. So if I wanted all these to be pointers, I'd have to say B3 is a pointer, B4 is a pointer, B5 is a pointer, and pbox is a pointer. So that's why you'll see some people locate the star in different places, is because sometimes you may lose the meaning of the pointer if you don't put it in exactly the right place. So let me put these back. So the reason why I butted up against pbox there is because I can't put it over here next to the struct, or else it's no longer that pbox is the pointer, it's B3 is the pointer. So the pointer means the next thing that's encountered is the thing that's the pointer. I also like it up against, because that makes me think, oh, it's a box pointer. All right, so hopefully that's not too confusing, but that's what I'm doing in the linked list code. Is I have declared a struct, just like I did on Tuesday's video, and then I've immediately created a pointer to it called head. So now I'm going to explain what I mean by the head pointer from the linked list perspective. But anyway, that's the new sort of programming setup that we haven't seen me do before, is declaring a struct and immediately declaring a variable of that type without separating the struct. I could, if I wanted to, put the struct separate from the slist class, but because I don't really need it anywhere but in the slist class, I'm just going to define it in there. Okay, so now let me talk about what this head part is before we start writing some code for this lab. The camera's dead. Hopefully it catches up. Come on, camera. Okay, so the other day I drew a picture like this, and I said linked list. I have a tablet now, I just haven't set it up. Linked list is kind of a concept, and what really is the data structure is a bunch of nodes. 10, 20, and 30 are just examples of the data. So it's really the nodes that are the data and the data structure. The linked list is just a concept referring to a set of nodes. But if we're going to write code that allows us to manage a set of nodes, we need some means of keeping track of where the nodes are, as it were. So what we're going to do is we're going to add a pointer to a node that we're calling head. And what head does is it allows the linked list, which is managing nodes, to keep track of where the first one in the chain is. So the head node is the first node in the chain of nodes, and that allows the linked list to access that node and then step through the nodes. It can also access this node for the purposes of adding new nodes or removing old nodes, retrieving data, that kind of thing. So linked list is kind of a manager that uses this one reference to keep track of, okay, who's the first node in the line? If I can get to that node, then I can use the links between nodes to step through the chain. So that's what this head thing is that you're seeing in code. The thing that's highlighted on the screen next to us. Okay, so takes some getting used to. You will get used to it over time. The pointers are going to throw you off a little bit for a while. But basically, we're going to write a set of functions that we call a linked list, which allows us to manage a set of nodes that's been chained together. Initially, when we first set up a linked list, there's going to be no nodes in there. And the linked list is just going to have this reference set to null. So when the linked list head is null, that means that there's no nodes being managed right now. It's an empty linked list is what we call it, because there's no nodes and hence no data. That's an empty linked list. The other thing that you're seeing in code over here to the side, this size variable. The size is simply a counter where we're going to keep count of the number of nodes that we currently manage as our linked list. So every time we add a node, we'll increase the size by 1. Every time we remove a node, which we're not doing this week, but we will eventually, every time we remove a node, we'll decrease the size by 1. So that size thing is really just a convenience that's keeping a count of how many nodes are being managed right now. Okay, so I'm going to hide that drawing. Hopefully by next week I'll be comfortable enough to use the drawing pad for that. Let me do some cleanup. Okay, so the size is just the linked list keeping count of how many nodes am I managing. The head is the linked list saying who's first in line. And then the linked list can use that reference to the first node in line to manipulate any node in the chain that it wants to. Okay, so let's start implementing these functions. I'm going to do them one at a time, so hopefully the jumping back and forth, no, let's just grab them all. Let's just grab them all. So like you've seen me do before, from the .h file, I'm going to copy all the function headers. And then I'm going to paste those into the .cpp file. And I'm going to leave the comments for now so that I remind myself what it is I'm supposed to do. I missed one. I left one behind. I'm going to do that again. So grab everything from toString through the constructor, which I forgot. Okay, that's all of them. 1, 2, 3, 4, 5, 6 function headers. I'm going to pull the comments out once I start doing implementations. So hopefully you have been consuming some of these videos and you know what happens next. What happens next is I'm going to stub out all these functions because I want to get compiling as soon as possible. So the first thing I do is I do the class name : step that I attach to every function in here. Because if I don't do that first, I just know I will forget to do it. So I just do that first. Then I'm going to stub out the functions. Constructors don't return anything, so a stub can just be an empty function. Notice, by the way, I took the semicolon off. Semicolon's gone because it doesn't do anything when you define the function. Semicolon off, empty block. The push front function also returns nothing, void in this case, so I'm just going to, the stub will be an empty block. This front function returns an integer, so to stub that, I'm just going to give it any integer. I often use 0 or -1 or something like that. Remember, that's a stub because I just want to get to where I can compile. The getSize function returns an unsigned integer. Well, that can't be a -1, but I can use a 0 just for a stub value. empty. I'll return false. Doesn't really matter. You can return false or true. It just needs to be a bool for the purposes of stubbing it. And then to string down here, let me push that up. So that returns a string, so I will just return an empty one to start, to stub it out. Now I'm going to go compile it and run it. I would expect, because there's at least one pointer in here, if you remember, I'm back in the .h file now, but there's this head pointer, and if there's a pointer somewhere in here and I haven't written any good code yet, it's likely that the first time I compile and run this with only stubs, it's going to crash. So I just expect that that's going to happen. If it don't, then I would just consider myself lucky. So let's see. I need to, well, let me see what my source files are. So I need to compile lab10.cpp and slist.cpp. I'm not compiling the .hppp or the .h because you don't. I've never figured out how many times I need to say this for people to stop doing it. So I'll put it here in the video, and maybe you can stop and replay this section if you're having this problem. You don't compile .h files, and you don't compile .hpp files. You don't. If you do, you're going to get an error, and then you're going to email me, and I'm going to say, didn't you hear me go on in the video and in class about this? So how do you get .h files and .hpp files into a program? You include them. They're headers. But if you have .cpp files, then ultimately they all have to be compiled. So there's the two CPP files. I'm going to change the name of the output to be lab10.exe. So, and I'm making a big deal out of this because for some people, for some reason, a lot of people seem to struggle with remembering this. So maybe if I just make a big deal out of it, eventually you'll remember. If you don't already remember. So you compile CPP files, you have to compile all of them, or you're going to get an error because not all the code is there. But you do not compile .h files. You include them. This is a catch program, so you're going to have to wait this one out for a sec. We expect, because of that head pointer that I haven't written any code for, that this is probably going to crash when I run it. But it compiles, and that's what I was going for. If I can get it to compile, then at least I'm on my way. So it didn't crash, which is a miracle, but it didn't pass much either. Somehow, magically, I passed 3 things just by dumb luck. But that's what I want. I want to get to compiling as soon as possible. Okay, so now let's start working on the actual code. So you're going to see my workflow is to do the easy stuff first, the things that I think are easy, at least, because I like the sense of progress that it gives me. So the constructor for a singly linked list, it needs to, for our singly linked list, we have a size, and we have a head pointer. That's really all the linked list does, is keep a count of how many nodes it's managing, and then keep a reference to the first one so it can do work on the chain of nodes. The size should be fairly obvious. That's 0. There's no nodes when you first start a linked list up. It also tells me to do that. And then head, since I don't have any nodes to keep a reference to start, well, that's just null. So as far as I can tell from the documentation, that's all I need to do. Plus, I know those are the only 2 data members that the linked list actually worries about. Remember, the list ultimately is the nodes. So that's where the sort of the good data is, but the linked list has a couple of pieces of data that it uses to do its management work. Okay, so I'm going to go recompile and rerun. So one function, compile and run. Still could crash at some point along the way, but I'm hoping at least that occasionally I'll pass a new test. I'm not passing any more than I was, but I'm not crashing, so at least there's that. Okay, push front, harder, let's put that off. This is get the piece of data. So push front means attach a new node at the front end, at the head end of the list. We're not going to do that one, that's a little harder. The front function is supposed to return the value that's in the first node. So remember, the linked list is just keeping a reference to one node of potentially many. So all this does is ask the list to go to that first node and retrieve the data. That one's a little bit harder, so I'm going to come back to it. This one's super easy. Get size, because all that is returning. Oops, I already had that word. It's just returning the size of the linked list. So that's low-hanging fruit. I'm going to go compile that again. Mostly I just want to make sure that I'm always sort of pretty close to the last time I was still compiling. And then I'm always crossing my fingers that I'll pass a new test somewhere along the way. Still passing and failing the same number, but it does compile, so that's a plus. Okay. So this one's pretty easy. Well, what determines if a list is empty? There's two ways to do this. You could say when the size of a list equals 0, or you could say when the head pointer is a null pointer. Totally up to you. To me, I just sort of make better sense of the idea that an empty list means that I have no nodes that I'm managing. So my count of nodes would be 0. So I'm simply going to return the result of that logic. If size equals 0, it will return true. And if size is not equal to 0, it will return false. So empty means that this is true. So there's another function. That one's pretty straightforward. So I'm going to go compile and see what I got. Doesn't crash, does compile, doesn't crash, it doesn't pass any new tests, but I haven't caused myself any new problems by any of that, so that's probably okay. Okay, to do any of the rest of these and have them mean anything, we have to go do a hard one now, and that is push front. So the idea of push front is that I get a value. I need to make a node to hold that value as the list, and then I'm going to take that node and I'm going to connect it to the other nodes that I'm managing. All right, so the first thing I'm going to do, though, is I'm going to make a node. I'll just call it in. Make a node to hold that value. That's the first job. When I get a value, is I need to make a node to hold it. So remember how linked list works. It is a whole bunch of nodes containing data that are chained together. So the value is the data in the node. And then the node I will use to chain things together. So the first job of the linked list in its management work is to take this value, which is a piece of data, and make a node to hold it. I'm going to go back real quick to the .h file and just show you where did I get this new node value thing? That's right here. So I'm using this constructor, handing it over a value. It's going to give me a node whose chain pointer is null and whose value is that value that I provided it. All right, I'm going to draw a picture now. Okay, so I'm going to take the circle out, but here's kind of what we have. We have head, which initially is null. That's sort of the state of the linked list initially. Head is a pointer to a node. Now the reason I wrote that is because I want to show you what my node that I just made is. So let me go back to here. Here's my new node. So do you notice that n is also a pointer to a node? So I also have is a pointer to a node, except for it's an actual node this time, because I made a new node for it. It has some value in it. Doesn't really matter what it is, but it has some value in it. And then it also made its chain link null. So the constructor for node made a node, put a value in it, and then nulled this chain. So right now I have two things. I have this n inside of my push front function, and then I have this head because you typed it wrong, capital L. No, I named the file, I just downloaded the files from my website and kept them what they were named on my website. So no, I didn't change anything. So you just need to pay attention to what you're doing here. Notice how slist is spelled. Capital S, capital L. So if you type capital S, little l, yes, that isn't anything. In this code, it's capital S, capital L, list, just like that. And I downloaded the files. The other question, I downloaded the files just like they were on my website. So you might be able to see it on your browser, slist.cpp, all small letters, slist.h, all small letters. Now last week I did make that mistake, so you're right to sort of be on the lookout for that. But this include here, that needs to match how I saved it on my computer. So just kind of pay attention to the way things are spelled. If you saved it as something other than slist.h, then you need to change your include. But if it were me, I would just download them as they were. Okay, and probably that other slist was a typo. So just pay attention to typos, and programming those things, of course, matter. Okay, so I have in my code, inside the function, I've made this n. And then my list has this head that's pointing to null. So to push a node onto the front really means to connect a node at this head. So for now, all I'm going to do is say this head equals n. And when you say a pointer equals something, I find it helpful to process it in my brain as this head points at something. So the head pointer points at what? It points at n. So in the drawing, what I'm saying is head no longer points to null, but it actually points at the same thing that n points at. So right now, head and n point at the same thing. And that's what it means to push a node onto the front, is to connect that node to head. What happens to n, by the way, when push front returns? The n just goes away. But you still have the node. So I'm going to save that, and I'm going to run it, and we'll see if it crashes or if I pass anymore or what happens. Remember, it's catch, so we got to be patient at this spot. So no change, but no new crash, no new passes, no new fails, so no change yet. But I want to show you what happens now. What if we were to push a second time right now? So what if we were to push front twice? What happens? So if we were to call this function again a second time, here's our original one. I'm just going to number these in the order that they happen. So that's the first node, and then this one will be the second node. So if we were to do push front once, this would happen. But if we do push front a second time, then what would happen is this head comes down to point at this new one, and then this new one goes away, and this one is abandoned. So we just lost that node, and that's not good node management if you are just losing nodes forever. So the trick is, if there's already a node there, how do we connect a new node to it? So what we really want is this at the end. If we push front the second time, then the new node coming in will connect that head and then chain itself to what used to be at the front. And if we were to push front the third time, we'd want this. These all point to null. So every time we push front, we want to take the new thing and connect it at the front, and then keep track of that now newly placed node as the head of the list. Every time we push front. So the first node would be like this one, and then if we push front a second node, it would connect at the front and become the new head, and then a third node would connect at the front and become the new head. And notice how this chain just keeps growing. So we need to write code that does that. So let me put the first node back. Okay, and now we need to figure out some way to connect. We need to figure out some way to get this node right here so that this link connects to here, and then this head reference points to here. Okay, so this one's trickier. The thing to do, though, generally the thing to do with these kinds of structures is connect the new guy first. So connect the new stuff and then mess with the old stuff. So this is the old stuff. This is the new stuff. So I need this to go here. So I need to take this and point it at something. So the trick is, how do I get to this? This is n's link pointer. So in code, So connect the new one first. So ends link pointer, which is labeled as next, points at what is currently in the front. So I'm going to take this next and point it to the same place as where head's pointing. So now the new thing is connected. Now I need to take head and shift it over here. So head points at end, which it turns out I was already doing. So head points at N, which is a prettier picture. That would then be head 2, 1, no. So that would be, that's what this mess is doing. And then when the function, the push front function ends, the end goes away. The node doesn't, but the end does. And then I don't know if anyone caught me on this yet. I didn't do all the steps. So that's the job of the list. Make a node, connect it into the list where it needs to be, and then adjust the list however you need to adjust it so that that head marker is referring to the correct place. Now the other thing that needs to happen here is that we need to increment the size of the list because we just created and connected a new node at the front. You may or may not be wondering this, but if you have wondered why are we adding things to the front first, it's because that's way easier to do than adding things at the back, which is way easier to do than adding things in the middle of stuff. So this is by far the easiest place to attach new nodes, is at the front. So we make a node, we connect the node's link pointer to the front, and then we move that reference to the newly attached node, and then we increase the counter by 1 because we just made and it connected a new node. Okay, so now I'm going to go, you can't see that, can you? No. So now I'm going to go compile that and run tests and see if I get any joy out of it by passing more. Still wouldn't be surprised if a crash happens somewhere because of the pointers and the incomplete code. But we'll see. All right, so fingers crossed. I think that these numbers flip-flopped. I think that we were passing 3 and failing 5. Now we're passing 5 and failing 3. So that's progress. Okay. So that's push front. This takes practice. That's all I can say about it. If you want to maximize your experience and sort of ensure your own learning, you should probably be working ahead on the labs and trying things before you just sort of transcribe my answers, because creating a solution and typing someone else's solution are two different things, of course, so just sort of heads up. In this format, I still think showing you how I'm getting the solutions is probably the best way to do it, but all the labs are there, and it would be a really good idea for your own learning to challenge yourself and sort of look ahead constantly and see what you can solve, or at least try to solve something before we get there. Because right now, if you're just typing what I type, then you're just getting to be a better typist. Okay, which would be a bummer. So there's that one. It compiles. I passed some more tests. That's no guarantee yet, but it's a start. Okay, so now front. This one is actually not that hard, but I wanted you to understand what front means. What front means is give me the data at the front. And the data at the front oh wait, no, I can just move this down a little bit. The data at the front is the data in the node that head refers to. So if I were to get the front in this situation, the value would be 1. If I were to get the front in this situation, the value would be 2. And if I were to get the front in this situation, the value would be 3. And we also need to protect against getting the front in this situation, because there is no data, because there's no node. So we need to make sure we protect ourselves against some effort to retrieve the data from the front node when there is no front node. So that's what this exception is about, when the list is empty. So there's two ways to do this. You could say, if this empty, because we have a function that already does that, then let's just do that to be in the habit of it. So if my empty function returns true, then I need to throw an exception. Let me just take that. That's why I put it there, is to make it easier for all of us to just grab it and do that. So if the list is empty, I can't give you any data from the front. There is no front. And I can't really return any value that would tell you that, oh, something went wrong. So I'm just going to throw an exception at you, telling you that what you did was naughty. Okay. If that doesn't happen, then I'm safe to return the head's data. I think it's called data. Value, the head's value. So head is a reference to a node, and I will use that reference to get the value out of that node. That's what the front is. But only if we're not empty. So that one's also pretty short. Let's go to the compiler, see if we still compile, and then cross our fingers that maybe we're passing more tests. Passing 7 and failing 1, so that's huge progress. And in fact, the only thing that's failing right now is the toString function, because I hadn't written it yet. So I actually sort of previewed this function on Tuesday, which is a problem of starting at the first node and stepping through until we reach the end of the list. Let me see what I did for string stream stuff. So I chose to use the output string stream, which is fine. It's the same thing for all intents and purposes. So I have an output string stream that I will, how about call it output, and then I'll stringify it at the end of doing work. If you're more comfortable with a regular old string stream as opposed to a string stream for output, but they're going to work the same. Oops, I didn't want to do that yet. Okay, and what I'm being told here is to print them out. So a value from a node, a comma, a value from a node, a comma, a value from a node, a comma, and so on down to the end. So the way we do this is the same way I did it on Tuesday. And let me draw a picture and show you a picture of what it is that I'm about to do. Oh wait, you can still see my paper. Okay. So I have this head, and then I have nodes, which has values in them, but I'm just going to say like 30, 20, and 10. So the thing to string stream And specifically, oh yeah, thank you, good catch. The string steam. Thank you for catching that before the compiler did, because I would have been frustrated at myself. So good catch. String stream, indeed. Okay, so I'm about to iterate my chain of nodes. And I want to be very careful to not alter this head, because if I move this head, for example, if I were to accidentally move it over one, this node is still here, but I can't get to it anymore. So I need to be very, very careful that I don't move that head pointer unless I really mean to. And the only time I really mean to right now is if I attach a new node. So I need to be careful that that doesn't happen. So the way to prevent that from happening, accidentally moving that very important head marker, is to give yourself a temporary one instead. So I can make myself a special marker pointer starting at head, and then I can move the marker around at will without affecting the actual list. So that's how I'm going to go about this. I need a marker that points at head. So it's going to be a pointer to a node, and it points at head. Now I can move the marker around and not jeopardize that head pointer, this head. Not jeopardize that head marker, because if I did that, I could break my chain or make it appear that I'd lost nodes even though I hadn't. Okay, so start there. The way to do this kind of iteration is to I'm going to show you the step part first. So usually you say, while that marker is not null, then I just move it over. So take it and point it at the next one over, repeat. Point it at the next one over, repeat. Point it at the next one over, repeat. Eventually, it's going to run off the end. Eventually, the marker is going to land on null, at which point our loop says, okay, stop. Okay. So before we move it, though, we need to grab the data from the node that the marker is pointing at and add that to our string stream. So before I move the marker, I'm going to take my output and I'm going to attach the marker's value to it, followed by a comma. Yeah, you can see that. So followed by a comma. So I'll grab a value, comma, grab a value. Well, okay, so it will do in this case, it's going to start the marker at the same place that head's at. While marker is not null, so it's not null, it's going to take the value at marker, which is 10, and a comma, and then it's going to move this marker over to the next one. It's going to grab that value. Oh, it's going to check for null. So while not null, it's not null. So it's going to grab a value, connect a comma, and then marker equals the next one over. It's going to check it for null, which it's not. It's going to grab the value and a comma, and then it's going to move the marker over. And it's going to check for null, and oh, we're done. It's null. There's no more data. So if my values were 10, 20, and 30 from the head back, this is what it would look like. You may see that there's an issue there, but let's see what happens. Okay, so we do not pass, and there might be some among you who see the problem, but I'll show you. So here's what my code did. Here's what was expected. And hopefully you see the difference. And it was also told to me in the comments. My code puts a comma on the end, whereas the test didn't want a comma after the last one. And it's also in the comments over here. If you notice, the example shows commas after all of them but the last one. So the trick is, how do I either prevent that last comma from happening or take it off after it's all said and done? What I found most people are comfortable with is prevent that one from happening. So if we pull the picture back up, of 10, 20, and 30, the one that shouldn't have the comma is the 30. And you might notice that what's unique about 30 is that its next is null. Its link pointer points to null. 10's link pointer points to something. It's not null. 20's link pointer points to something. It's not null. 30's link pointer points to null. So the nodes that point to a next not null get a comma. And the nodes that point to null next to null don't get a comma. But it's really the ones that have a neighbor get a comma. So we just need to write logic to do that. So I'm going to take the comma off there, and I'm just going to say, is there a neighbor? Meaning, does that next not null? Does it go somewhere? If that next is not null, then yes, there is a neighbor, and I want a comma. This is not actually the way I would do it. I would probably just use a substring and chop off the last comma, but I found that most people seem to be most comfortable with this approach. So I'm looking for every node that has a neighbor, and that's the code to do that, right? If next is not null, that means I've got a neighbor. And if I have a neighbor, then I need a comma. Catch. Catch is slow. All right, all passing. So one thing, and you'll note this, by the way, for much of the rest of the semester, we don't have that many functions anymore that are long, that have a lot of code in them. It's just the code is complicated. The best piece of advice that I ever got and that I think I can give is to draw pictures of stuff. Draw pictures of stuff, and as you write a piece of code, change the picture to match what your code is. It will help you understand what the code's doing better. It will also help you find bugs in your code, because you'll have to like move a pointer in your drawing, and you'll think, wait a second, if I do that, that breaks the thing, and it'll help you sort of identify where you've introduced a bug into your code. So I highly recommend. It was the thing that got me over the hump, was drawing pictures like this. If you have a whiteboard at home, that can be helpful because you can easily erase if we were in class. And once I get my tablet working, then I'll be able to sort of make prettier pictures, but hopefully that'll be for next Tuesday. But for yourself, I've tried index cards and pieces of string, and whiteboards I like the best, but paper works. You just have to keep track of what it is that your drawing means. Try drawing pictures of stuff. Most people will not do it, but the people who come to understand how this works and how to write code for it the fastest will be the ones who draw pictures. It's the best thing you can do for yourself to make sense of this. Okay, that's the whole lab. Yeah, that's everything that I do. So that's lab 10. which is due this week by Sunday. And now I'll sit here quietly for a few minutes or longer as needed to answer your questions. There's a tiny bit of a lag, you probably noticed. So sometimes when I move the screen around, there may be a lag from when you chatted it. Probably you're familiar with that. As I did that, by the way, I saw a thing I didn't like. That was just, it's legal but sloppy. They're on line 14 on my code. I want to be specific about when I'm referring to a part of the list as opposed to when I'm referring to other things. Which I didn't do. Let's see, where else didn't I didn't do it here. On line 26. And now I bet I can find it all over the place if I look. No, okay, that was it. I was sloppy on lines 14 and 26. Sorry about that. Thanks. Yeah, have a good weekend. See you next week.